discussion that we're going through as possible. From next semester onwards, I hope to get more, calculational stuff. Calculate scattering amplitudes and try to get more of a field. Okay, so fine. Okay, so let's return to the discussion we were having last time. You remember that at the end of the last class, we wrote down this scattering amplitude for string theory, and so basically what we had wanted to do was to compute the path integral over all world sheets with certain insertions in place. We converted that path integral over all world sheets to a path integral over the x fields and some closed fields plus some moduli. Okay, so the final answer was an integral over moduli, a path integral over x fields, and a path integral over the closed fields, so DC and D. Okay, then the things that we integrated over had a worldsheet action and had some insertions. Okay, so the worldsheet action was exponential of minus the Polyakov action. So that was just the action we started our discussions with in this course. But then to that you added the BC action plus B del C. B del bar C plus delta. Okay, the B and C came from they were the closest from K sheets, as we discussed in detail in the previous class. All that. Okay, and that was it. Pulchinski finds it convenient with some normalization, which we will follow him with. I'm not going to write that down. Of course, it makes no difference because you can change the normalization by rescaling the fields B and C. So it's physically. Okay, and then this was the action. We also had some insertions. The insertions were the following: for every factor of the for every moduli field, we had an insertion of del G by del Tm. Del G by del Tm times B. Okay, so what was this? Let me write it down. Okay. Remember that B started its life as a two tensor. Okay, so the insertion that we actually had would be alpha beta square root G integral del G alpha beta by del Tm, and then we have product over M. So one such insertion for every field. And then we've got a particular conformal basis to write this out, so we should write out this insertion in that conformal basis. Essentially, this becomes a factor of B in it. Okay. And then we also had an insertion which was the product over C times C tilde times the vertex operators and the number of these guys was the number of conformal killing vectors. The number of diffeomorphisms that wasn't fixed by a positive conformal gauge. So you have product over these guys, and then you also had a product over integrated vertex operators for the remaining insertions. Okay, that's this down on the schematically, but this is the final form of the answer for the S matrix, for the S matrix element that we're interested in strictly. Okay. Now, this class and the next we'll analyze aspects of this formula, elements of this formula in various ways. We will want by the end to show this formula, both by analysis of examples and for formalic arguments, that this formula is a sensible formula defining sensible scattering processes in quantum field, in an extension of a quantum field theory. We'll want to show many things about this formula. But even before we can start talking about some of its properties, there's some formal discussion that I need to go through. Okay? And this formal discussion is a discussion of the BRST symmetry of the action, of this action. Okay? So, we're going to get back to the discussion of various aspects of this formula in a bit. But in order to start talking about aspects of this formula, and especially as the question of what vertex operators here you are allowed to put into this path integral, it will be very useful for us to have a better understanding of some of the symmetry properties of this action before we start. Okay, the symmetry property that we're interested in that has a name, it's called the BRST symmetry. Okay, and my discussion of the BRST symmetry of transformations of properties is basically very closely follows Kuczynski. There's a really, really beautiful discussion of BRST symmetry. It's so much nicer than the discussion you find in a standard field theory textbook. Okay. So we're going to put this action on hold for a moment and ask a slightly more abstract formal question that's relevant to any gauge theory in any gauge physics. Okay? And the question that we're going to ask is, suppose we take the gauge theory and quantize it using the Faddeev-Popov method. Okay? Is there well, we ask the question because the answer is in the affirmative, but the question we ask is there an extended symmetry? An extended symmetry of the gauge fixed action that, involves the coasts as well as the matter fields. Okay? And the reason we ask this question now is the answer is yes. And this is the thing that I want to describe to you, mainly in this lecture, and to show you how it applies to the string action. Okay? So, the first part of the discussion of this lecture will be formal and abstract and apply to any gauge theories, but that's not necessarily the string. So let's set up some notation. Suppose we've got a theory whose various fields I denote by phi I. I'm going to use completely, following Kuczynski, I'm going to use completely abstract and compressed notation. So this I index could be a flavor index for the field, but it could also be a space index for where the field is. In general, in field theory, phi I would be phi I index, but this I includes both position of the field as well as any other quantum numbers. Okay. This gauge theory has gauge symmetry. So let's say that the transformation properties of these fields phi I under the gauge transformation. So firstly, I'll use the symbol alpha to denote the various inequivalent transformations. Once again, alpha could be labeled by space-time point. Gauge symmetries are generally local in space. So alpha could run over a continuous number of variables. Okay? I'll use the symbol delta alpha to denote the variation of any quantity under the gauge transformation parameterized by alpha. Okay? And in particular, delta phi I will represent the variation of phi I under the gauge transformation parameterized by alpha. Okay? And fine. So, alpha is a parameter that labels infinitesimal transformations. Yes, so alpha is a label in the D algebra of the gauge transformation. But remember, this is a gauge transformation, it's a label of not a algebra of a group, but of gauge transformations. There's an alpha for every point in space as well as whatever it is. Okay? Good. So, if we were just discussing gauge transformations, we need no other structure. We were discussing gauge fixed actions. Okay? So, I also have to tell you what gauge fixing condition I've used. Okay? So, let the gauge fixing conditions in my theory be denoted by Fa. There are some functions of phi I, and my gauge fixing conditions are chosen to be Fa of phi I is equal to 0. Okay? Now, in implementing the Faddeev-Popov method that we described for string theory last time, you just take the discussion we had 2 lectures ago and apply it to any gauge theory. The whole discussion goes through. So you remember what the final conclusion was. The final conclusion was that we put in a delta function. We put in a delta function that enforced that all gauge fields were on shell that obeyed this equation. in analyzing this path, the path integral with the delta function, we found it convenient to exponentiate this delta function. Okay? So the final action was, I've got an SYM, the angles action, the gauge, the original action, which is a function only of phi I, minus I times, and I'll call it BA, okay, this is the part of the action such that the integral over BA encloses delta function of FA is equal to 0, FA of phi I, and then plus the cos part, which came from the Polyakov determinant. Now remember how we got the determinant. We took a small variation of FA with respect to a gauge transformation. We wanted the determinant of that rather than the inverse determinant. So we did a Gaussian integral over the small variation with respect to two anti-commuting fields. Okay? So the small variation of FA is delta alpha FA, and then in order to get the determinant, we multiply it by some field C alpha and some field BA, both of which are taken to be anti. Okay? So for any gauge theory, we have the structure. The gauge fixed action has the original action, has the path that enforces the gauge fixing condition by doing an integral over the Lagrange multiplier, and has the Faddeev-Popov curve. In order to derive this, I'll ask you to rerun the derivation we went through in the case of string theory in your head. But in the abstract case, it's easier in the abstract case. You don't have to figure out what the variation is. It's the variation. Okay, it's a 5-minute exercise which we won't go through again. It's just the same logic, but I'm going to ask you to read it. Anyway. Okay? Maybe we should at some point have a discussion session in class where I ask you guys questions, you ask me questions, I ask you questions, and we discuss things. But maybe that would be useful at some point. But let's move on. Okay. Now, this is the action. Now, I want to point out that in complete generality, this action has a global symmetry. Okay? This global symmetry is a name, so the BRST symmetry, and variations under the symmetry are denoted by delta B, where B stands for BRST. Okay? So in order to define the symmetry, I'll tell you what the variation of all fields under the symmetry is, then we'll check that it's symmetry. Okay. So delta B of phi I is equal to minus I times C alpha delta alpha. Okay, delta B of BA is 0. Delta B of BA is equal to BA, and delta B of C alpha is equal to minus I by 2 F alpha beta gamma C beta C. Oh, I have to tell you what F is, so let me tell you what F is. So F is the structure constant of this gauge symmetry. So delta alpha combined with delta beta to NP is equal to F alpha beta gamma. Okay, that's the definition of F. Okay, it is the meaning of everything we've written down in the book. I should check the minus. Oh, so I've got the minus sign. Okay, this one's a plus. Is the meaning of the equation to the bottom here? We're going to check whether they work or not, whether they have interesting physical properties, but what this means is here. Look, I have you.
It's an infinitesimal transformation.
Yes. So if you want to really make a symmetry, if you think of it as a variation, you multiply by the infinitesimal parameter.
Yeah.
Multiply by an anti-commuting infinitesimal parameter. Okay, you should multiply everything on the right hand side here, correct? By an epsilon, which is anti-commutative. If you, right. Okay, I'm going to use this symbol delta though for the variation without the epsilon. So you should think of the variation as epsilon times delta B of whatever, of field. Okay, I find that useful just as a matter of notation.
Okay, this is just.
Yes.
What is the way of defining what is your BRST charge?
The BRST charge, will be the thing which is anti-commutative of these fields gives you this stuff.
Okay, so this will be the operator corresponding to the delta.
Corresponding to delta. The operator such that the anti-commutator of phi I will be delta B. Yeah, that's the reason I find it convenient to use delta with the constant. Okay, good. So, now the first thing we're going to notice is that the angles, that the action we wrote down on the board can, in terms of this operation delta that I've defined, can be written in an interesting form. I claim that we can rewrite S as equal to S angles plus there's some I which we'll get straight in a moment, but delta B of BA. So comparing with this sign here, I'll put a minus. Okay, let's check. Okay, so what we have, so SC angles is SC angles. This part is this part. So if this is true, this will affect some of these two terms. Okay, let's check that. Delta B acting on BA, delta B acting on BA. Okay, wait. Now that these things are anti-commuting, I should get the order as well. Okay, I hope I got the order. I will check. Okay, so delta B acting on BA is equal to capital BA, and so that gives me the system here. On the other hand, delta B acting on FA is what? Delta B acting on FA is okay, so firstly I become minus sign because it goes through an delta B, which itself is an anti-commuting operation, goes through an anti-commuting field. So I get plus I times BA, okay, times the variation of FA. Now how does FA vary? It varies because phi varies. So the first thing you want, you see, the first thing I should have said is that notice that the action of the BRST transformation on the field phi I is simply the action of a gauge transformation on the field phi I with gauge parameter C alpha. Okay, so formally, the variation of any function of phi i's under a BRST transformation is the same as the variation of that function of phi i's, okay, under the gauge transformation generated by C alpha, whose infinitesimal parameter is C alpha. Okay, so this thing is the same as C alpha times delta alpha, because by definition delta alpha was the change of the quantity alpha under the gauge transformation.
Although you can view that change as a change where the ghost fields are local fields, right?
Yes.
So I mean, in spite of that, the BRST symmetry is a global symmetry.
It's a global symmetry.
The epsilon is constant.
Yeah, epsilon is constant, exactly. You see, because, exactly. You see, this is not a new field, a new parameter that you're putting in your problem. It's a field of the theory. There's only one BRST charge. There are not many different BRST symmetries depending on some function worth of parameters. There's one BRST. Okay, good. So, because the gauge transformation is minus I times C. Okay, so we put that together, we get minus I times I is plus, we get plus BA, which is the same thing as here. Okay, so the first thing we've done is we've checked that the action is equal to Sym plus delta B of minus I times delta B of BA times B. Okay. Now the next property of this variation that we're going to study is that this variation squares to zero. Okay. So I want to declare that delta B and delta B on any field is equal to zero. Okay, let's check this. In order to check this, we check this field by field. Okay, first let's discount the simple ones. Let's do it at BA. Well, since one variation is 0, two variations are certainly 0. Let's do it at little BA. The first variation is BA, the second variation is a variation of BA, which is 0, so that's good. So the non-trivial ones are these two guys. Okay, so let's first try it with phi. Okay, so what we want to check is the delta B of the variation of phi I. So if it's 0, it's 0 up to constants as well. So I drop minus I. So delta B of C alpha delta alpha phi I want to calculate this and check whether it's 0. Okay, so let's calculate. So this is two terms. The first term here is it comes from the change in C alpha, and the change in C alpha is I by 2 F alpha beta gamma C beta C gamma, and then you multiply by delta alpha. Okay? The second term, where we pick up a minus sign because we go through an anti-commuting object, and then we perform the variation. We perform the BRST variation of phi I. So we get minus delta alpha of C beta, let's call it delta beta minus delta alpha of C beta delta beta of phi.
Which we have this C
And this is C alpha. Sorry?
minus I can say.
And a minus I. Thank you. This is because this had a minus I. Thank you. So this, let's make it a plus. Okay. Now the next thing we use is that C with itself, anti-commutes with itself. Okay? So this delta alpha delta beta, we can rewrite as a sum over commutator plus anti-commutator. Each by 2. Commutator by 2 plus anti-commutator by 2. Okay? And it's only the anti-commutator piece that survives because C is anti-symmetric with itself. Because C is anti. Is this clear? So we've got. Oh, wait a minute. Wait a minute. Sorry. So this is delta and C is and delta. Just let me take a right on that, right? Sorry, hang on, please.
The anti-commutator is symmetric under the indexing delta basis, so C alpha and C beta will be 0.
Yeah, that's right. I'm just wondering whether I should really have the C inside this delta. Hang on. Almost certainly not. So just.
Okay, I think what we have to. Okay, I think what we should have done is that the C beta, del beta, the whole thing would have come out of del alpha phi. Del alpha phi is a function, and we are looking at the gauge transformation of the function. So you just get minus I C beta del beta of del alpha phi.
Yeah, exactly. I think you're right. I think you're right for exactly the reason that you said. You know, it's an infinitesimal variation. In particular, some linear function of phi's. So we could write this in matrix form if we wanted. This is some matrix del alpha phi is some m alpha ij of phi j, and this second del acts only on that phi j.
No, on the whole, del alpha phi itself is a whole function, and we want the gauge transformation.
Exactly, because m is independent of phi, because infinitesimally it's a linear function. So it acts only on that phi j. So it's really okay. Okay. Now the next step that I want to do is to and now I'm getting okay, this goes good. Okay, good. The next step that I do is replace this by anti-commutator of delta beta with delta alpha. Okay, and then I get a factor by 2. So I can replace this by 2 an anti-commutator of delta beta with delta alpha. Okay, and then at the next step I use that the anti-commutator of delta beta and delta alpha is f beta. So this then becomes f beta alpha gamma delta gamma phi, which is minus this, changing W indices. Okay, phi I. So this thing is the same. Okay, as you see, basically, when you think things through straight, the only difficult part of your calculations is to keep track of minus signs. So often difficult to get confused about your minus signs. Okay, whenever your life depends on it, you think that through carefully. Otherwise, it's a painful thing to keep track of. Okay. Fine. I should have cleared. Okay. I'm going to leave as an exercise the checking of the double variation of C being 0. Let me just give you the main steps. Remember that the change in C itself, delta B of C alpha, was proportional to F alpha beta gamma, C beta C gamma. Okay? So what you want to do is to check that the variation of this is 0. Now the variation of this is 2 terms, one with the delta acting on the CB and the second with the delta acting on the C gamma, but each of which will be the same up to a factor of 2 when you work it out carefully, keeping track of the minus things. Okay. So any one of these 2 terms will be of the following form: C alpha beta gamma, and then let's do the variation of beta. C beta, let's say some theta phi, and you'll get C theta C phi C gamma. So when you take variation on both terms, add them up, you get something proportional to this. Okay, the 2 terms will be the same. Okay. Now this thing here is an because C is a completely antisymmetric. This is a completely antisymmetric product of 2 M squares. Okay? Which is 0 by the Jacobian entity. Okay, so this is the main idea. I want you to convince yourself that in detail that all this is correct. Okay, so we're not going to spend time. Okay, great. So we checked that the BRST charge squares C. Fine. Now why is that important? It's important for several reasons. The first reason it's important is the following. You remember we started out this whole discussion by saying I wanted to find out a new symmetry of this action. So far I've not talked about the symmetry of this action. I'm not showing you the action itself is indebted under this transformation. But now from everything we've seen, it's obvious. Because remember, the action was equal to SYM plus delta B of BAF. So let's check how the action varies under BRST. The variation of this part is 0 because the BRST charge squares to 0. Yes, take two variations of anything, let's see. What about the variation of this term? Variation of this term is 0 because SYM was a gauge varying function of phi i's, and the BRST transformation on phi i's is a gauge transformation labeled by a parameter C alpha. Okay? So both these terms of the action manifestly have 0 BRST variation. You know, if you need practice in dealing with anti-commuting fields, algebra with anti-commuting fields, I'd advise you to just take the expanded version of this part and explicitly check that when you do the variation, the BRST variation, you get 0. Again, the only difficult thing in that calculation is, well, it's not difficult, the only painful thing in that calculation is keeping track of minuses. Okay, so that's the first thing. We've seen that the symmetry, that our action, the action that we've written along with those fields, has a new symmetry in it. Okay, it's a symmetry. First, notice that it's an anti-commuting symmetry. It's a symmetry whose parameter epsilon would have been an anti-commuting field. Why is that? It's because, for instance, you see that the statistic, the commuting and anti-commuting nature of each field has been changed in the symmetric transformation. For instance, the change in phi is proportional to C, which was anti-commuting. So you need an anti-commuting parameter multiplied. Okay. But now, okay, so we've seen that we've got new symmetry and that the symmetry squares to 0. So the generator of the symmetry, whatever it is, we call it QB, and this thing squares to 0. Okay. Now there's something that I want you to remember, and the thing is this: you remember that C alphas. You remember, there's something about the reality properties of C and B that I want to remind you of. Okay? The thing that I want to remind you of is that this BC action came from looking at a determinant of the gauge fixing term, the gauge fixing term under an infinitesimal gauge transformation. The gauge transformation was real. Okay? And each of these gauge fixing parameter terms are also real. It's not like we've got a complex valued set of gauge fixing terms. Okay? So in our derivation of the BRST action, where we had an integral representation for the inverse determinant that we were interested in, we were doing an integral over commuting real fields. In order to get the representation of the determinant, we had to transform that into a path integral over anti-commuting but real fields. Okay? So because of that, this C parameter, the C field and these B fields that we're talking about here are real fields. Okay? So because of that, the BRST charge itself is a real symmetry. Complex conjugated, you get the same thing. For instance, look at the transformation of phi. Phi is C times delta phi. You complex conjugated, both things go back to themselves. Okay, so the quantum analog of that statement that will be that this operator QB is a Hermitian operator. Okay, in explicit examples where you actually work out, what the commutation relations of all fields are, write down an operator expression for Q, you can check this explicitly. For instance, string theory will see this very explicitly. But what you always expect is that this symmetry here, QB, will be a Hermitian operator. That's QB dagger will be QB. Okay. Now that we have this nice symmetry, along with this Hermitian property, we can now analyze some, consistency properties of correlation function calculations in gauge theory. Remember that the gauge fixing function that we fixed in order to facilitate calculations was completely arbitrary. We chose this FA in a completely arbitrary way. if any calculation we do reflects properties of the theory and not of arbitrary choice of gauge fixing parameter, then let it be that any calculation we do is invariant under the choice, under, let's say, small deformation of this FA gauge fixing function. Okay? Any calculation that depends on FA is a calculation that talks about the way we set up the calculation rather than the theory. Okay? So, now let's see. Remember that S was equal to SYM plus delta B BAF. Suppose we change FA a little bit. How does the action change? Okay? So the action, under a small change of FA, the action changes by delta S is equal to delta B of BA delta FA. But this delta has nothing to do with BRST transformation. It's just a small change in our representation. Okay? Now, this we can write as the anti-commutator of QBRST with BA times delta FA. Because by definition, the BRST operator is the operator such that its anti-commutator of any field is the small deviation under a BRST transformation. Okay? So now let's say. You see, suppose we were trying to compute some amplitude between an initial state and a final state, and I want to see whether that amplitude changes if I perform a small BR, if I change my gauge fixing condition a little bit. Okay, so suppose my final state was psi fin, and I'm doing some e to the power minus blah blah blah, so propagator calculation, and I have some psi. Suppose I change my BRST charge a little bit. Sorry, I change my gauge fixing condition a little bit. I've changed the action and therefore the Hamiltonian of my system by something proportional to an anti-commutator of the BRST thing, but something. Okay? So what will the change in this amplitude be? The change in this amplitude will be proportional to psi fin times QB BA delta F. Right, to first one. Now, see, we want to demand that this quantity is 0 for arbitrary delta F. How can that be? The only way that can be, because delta F is completely arbitrary. Okay? The only way that can be, how do we do that? But this must be some condition on the states. It won't be true for every state, right now, for sure. Must be some condition that you impose on states. And the only way this can work, because delta F is completely arbitrary, is that must be a condition involving QB in the states. Now, since delta F is completely arbitrary, we don't want a condition on QB times this time state. So it must be a condition of QB acting this way. Okay, so let's write this out in more details. This must be, and QB BA delta F A plus BA delta F A QB. Okay, now since this kind of commission, we can write this in the first term. So we can write this in sum of two terms. We can write this as QB on psi fin BA delta F A psi in plus psi fin BA delta F A QB on psi. Okay. Now, more or less the only way in which this can be zero for arbitrary delta F A, okay, is for psi fin and psi in both to separately satisfy the condition that they are annihilated by QB. Certainly, if that is true, this will be zero for F A, arbitrary delta F A. I'm not sure. Maybe, if this is really completely arbitrary, it's probably possible to prove that this is the only way to happen. I haven't thought that through yet. Okay, but anyway, so what we're going to do then is, with this action, we're going to make the following cut. We're going to say that, look, states, we set up some calculation. Okay? This calculation can then be interpreted in some Hilbert space. Whether we've got a path integral, you can take the path integral, slice it on constant time slices, and give a Hilbert space interpretation for that path integral. Or at least, if the path integral is reasonable enough, you can always do that. Okay? But not every state in this Hilbert space that you obtain by slicing this path integral is going to be treated as physical. For instance, that's manifestly clear, right? Physical states in the Hilbert space should be states that contain oscillators only of the phi I fields. The CMA things, which is tricks, we put those fields in to help our path integral calculation. But clearly, if you have an oscillator just for the C or the B's and it acts on a state, clearly that's something physical. It was some calculation trick, it was not something physical in nature. So not every state that you get by taking this path integral and slicing it will be treated as a physical state. Only those states that are annihilated by QP will be treated as physical. Is this clear? If we make this ansatz, then we're guaranteed that something very good will happen. And the something good that will happen is that any calculation we do will be invariant under a choice of H. Okay? And therefore, give us a calculation about the theory rather than about a procedure calculation. Similarly, if we were interested in an operator acting on these states, we will also require that all correlation functions that are meaningful in this theory are correlation functions of operators that commute or anti-commute depending on statistics with the BRST charge for exactly the same reason. Okay, provided it commutes anti-commutes with the BRST charge, then we can take this up. You put some operator here, you can run this Q through that operator and it will annihilate the state. If it didn't, you couldn't. And the calculation would depend on the choice of gauge-fixing function. Okay? So at least it's very plausible a guess for how the Hilbert space. So I want to emphasize one thing here. Generally when you're dealing with gauge theory, you can often fix gauge or do some thinking before you do some careful thinking in your problem to understand what the Hilbert space is without all these hosts. So the question of what the Hilbert space of the theory is not a physically ambiguous one. It's a clear answer. What we want to do is something different. What we want to do now is the following. You see, there is this calculation procedure that is very convenient. It's a calculation procedure that involves adding new fields and changing our action. If you take the action for the calculation procedure, slice it take your integral, slice it, and associate a Hamiltonian with the time addition generator of that path integral. Okay? This gives you a larger Hilbert space. It's clear there's a larger Hilbert space because there are more fields. Okay? Now, we want to identify the original physical Hilbert space as some subsector of the Hilbert space of this larger auxiliary problem. Okay? And the claim we're making is that, well, this is at this level a guess, but it's a very natural guess. Basically, it could have been some subset of this, but you'd have to find a natural subset. In any given example, you can check whether it is actually the same thing, as we will do carefully for string theory. As you will say, please.
Also, what would the
We come. Yeah. But so the diagram is correct. There is an additional condition which we discussed in a moment. But so the condition we're going to the claim, yes. So there is a subset. But the claim is that the Hilbert space the physical Hilbert space of interest is given only by those states that are annihilated by Q. Okay, now we come to load diagrams. Okay, so is this clear? The motivation for this statement. Now we come to load diagrams. You see, let us now look at the following. Suppose we consider any state, okay, some chi in the theory that is of the form q times psi, where psi is any other state. Now, let's consider the inner product of chi with any physical state. Psi fixed and chi. Let's study this. Okay, so this is equal to psi phys q psi, which is equal to q and psi phys on psi, which is equal to 0 because physical state is annihilated by q. Notice that psi phys could have been any state in the world, any physical state in the world, including chi itself. Okay. So, what have we done? You see, we were interested in states. We said physical states are states that are annihilated by Q. Remember Q BRST square is 0. This is one very simple way of solving this condition that states are annihilated by Q. Namely, let's choose the state to be Q times any other state. Because Q square is 0, that will automatically be annihilated by Q. However, so we've got a large number of states which are BRST. Okay, so the terminology. Something that's annihilated by Q is called BRST closed. Something that is Q times another state is called BRST exact. Okay? So, any state that's BRST exact is also BRST closed. This is the reverse mean term. Okay. Now, states that are BRST exact are BRST closed, are in some sense physical, are physical by definition so far. However, they have zero inner product with any other physical state, including themselves. Okay? So now suppose I take two states psi. Two states, one state psi, and the other state psi plus q times. Okay, I should call it. Okay, anyway, q times alpha. Alpha is absolutely x. The inner product of these two states with every other physical state in the theory is identical. Because this part gives us. So, as far as physical measurements are concerned, and this is true also not just inner products but correlation functions with operators, all of which are BRST closed. Okay? So, as far as physical measurements are concerned, these two states are physically identical. Okay? Therefore, although both these states are physical according to our definition, okay, they must clearly represent the same physical configuration. So the true physical Hilbert space, if you want, one state per physical configuration, the true physical Hilbert space is more subtle than just the set of all BRST closed states. So the physical Hilbert space is Q is BRST modulo BRST. Okay? And that modulo means the following. It means the physical Hilbert space is the set of equivalence classes of BRST closed states, where any two states, BRST closed states, are treated as equivalent if their difference is BRST exact. Okay? So by modulo I mean this equivalence class. Is this clear? Okay? There is a completely analogous statement for operators. Remember that we wanted that an operator commute with the BRST charge. There's a very simple way of arranging that. Namely, choose the operator to be the commutator of some operator with a BRST charge. But two operators that differ by such a commutator give identical matrix elements. Because the Q on one side kills the first state and Q on the other side kills the second state. So any two operators that are equivalent up to commutator with commutator anti-commutator according to statistics with the BRST charge are physically equivalent. They give identical matrix elements and so are the same operator. Okay? So once again, the set of physically relevant operators in the theory should be thought of as members of BRST cohomology. By this operation of taking the set of BRST closed objects and modding out by BRST exacts for cohomology. that has a mathematical name. It's called cohomology. Okay, great. So just to summarize, in any gauge theory, once we gauge fixed, we've got a path integral with which you can which displays just the level of path integral and interesting symmetry. Okay, that symmetry is fermionic and it's coercive. Okay, the action of our theory is invariant under that symmetry, but more importantly, the change in the action of the theory under a change in gauge fiction condition is BRST exact. Because it's BRST exact, once we identify the correct physical Hilbert space, namely the Hilbert space of BRST closed states and BRST closed operators, because it's BRST exact, the two different Hamiltonians that you get by making choosing one choice of gauge fixing parameter or the other are the same Hamiltonian because they differ by BRST. Okay, great. So this structure which applies to every gauge theory in the world, when you gauge fix using Party-Popov and write out a path integral using Party-Popov methods, also applies, of course, to the action of the word problem of the strip. Okay, so now what we want to do is to understand in more detail the BRST transformation properties, the BRST symmetry and the word problem of the strip. But just so that the algebra is sort of simpler, we'll first do it for the point particle, where it's a little easier, it's a little more transparent, and then work it out for the strip. Okay, so let me look up the other side. Okay, so let's remember what the action for the point particle was. So S was equal to d tau x mu dot x mu dot by E and plus m squared E. Okay, so in what we did in the first two lectures of this course, we wrote down an action for the point particle, which, when continued to Euclidean space, takes this form. Okay, but now what we want to do is to treat this point particle example to deal with the quantization of this point particle in sort of fifth way. Remember, we had one lecture and we did 4 different ways of quantizing this point particle. We'll do one more. Okay? And the way we're going to quantize this path integral now is by the Party-Popov method, the BRST method. So we're going to do a path integral quantization of this point particle, but by choosing a choice of gauge. What gauge will we choose? Well, we choose the obvious one. We choose E is equal to 1. Okay? So according to the discussion we had today, what should we be doing? We should be enlarging this action. We should be enlarging this action to include an I times B, or perhaps minus I times, times E minus 1. Okay? That's the part that enforces this delta function. Okay? And then we should, in addition, add the part that is the Party-Popov determinant. Okay? So what's the Party-Popov determinant here? Well, you see, what we have to do is to see how E changes under a gauge transformation. Now, under a gauge transformation is a diffeomorphism in this case. So how does E change? E changes in 2 different ways. Under an infinitesimal gauge transformation, it changes, the first way in which it changes is that E is a function of parameters. So there is a change which is of the form, so under T is equal to T plus T is equal to T tilde plus F of T tilde. We will have a change in E proportional to F times del E, just from the fact that E is a function. But then E also transforms with a certain weight. So there will be another transformation that will be proportional to del F by del T, times E. Because E is the square root of the metric, and the metric changes with a factor like this. Is this clear? So the change in E will be the sum of two terms with appropriate relative coefficients, minus signs or plus signs. Okay? Now, what we want to do is to look at the variation of this quantity and multiply by a B field and a C field. The C field was this F field, the infinitesimal change. The infinitesimal change in the infinitesimal parameter that labels our infinitesimal symmetry transformation. Okay? So these two terms will give us what? They give us terms like B times del E times C. Okay? And we get plus B times E times del C.
C should be contracted with del.
Sorry?
C is contracted with del.
There's no contraction here, it's just one parameter.
Yeah.
Stack. One dimension. Okay? So then we do this, I'm just going to integrate by parts to get B dot EC. Polchinski has EBC dot. So sorry. Okay, let me try to do this offline. I'll get back to you next class. What my logic is leading me to is that this would be after the integration by parts, it would be proportional to B times E times B dot times E times C. I want to warn you that Polchinski has written the same thing with the dot of the C. Let's just continue. We'll see if we run into trouble with this. And definitely, I think it would carefully come back next class. Something very similar to this, but this is what I mentioned. I must be messing up. Okay, good. So now what we have here, it could be the next class. I'll come and tell you this is BEC dot for some reason that is escaped from me now. Okay, sorry. But okay, good. So this is the so Lognagham's suggestion was let's try to write this. Okay, let's try to write down the BRST variation as you said, and we'll see how it goes. Okay, good. So what is the BRST variation for all fields? Okay, that's quite simple. Well, let's see. Let's look at delta x mu. Delta x mu is just an infinitesimal change in x mu under a small diffeomorphism. So that just changes as with some sign convention. I times C times x mu dot. Right? Delta of B was 0. Delta of little b was equal to b, and delta of c. Okay, this is more interesting because what you have to do is now look at, we have to identify what f alpha beta gamma is. Okay? In order to identify what f alpha beta gamma is, what you have to do is to perform two different diffeomorphisms in different orders and see what you get. Okay? So suppose we perform a diffeomorphism generated by a function v, and then perform a diffeomorphism generated by a function g. Okay? Now, so what is the diffeomorphism in question? Okay, so suppose you say that t is equal to tau tilde, tau is equal to tau tilde plus let's call it f of tau tilde, and then you say that tau tilde is equal to tau tilde double tilde plus g of tau double tilde. Okay? Or you do it the other way around. You interchange the functions f and g. You want to see what difference you get. What difference you get in this quadratry definition. Okay? So the difference is going to come about when you put this definition in here. Or you do it the other way around. Okay? So in one case you get a change in tau that is g times derivative of f. But in the other case you get minus f times derivative of g. Okay? So you do this two diffeomorphisms in different orders, and you generate the effective difference diffeomorphism of this one. Okay? So now you want to put that in to f alpha beta gamma c beta c gamma. Okay? Well, this is simply so now you have to put both g and f equal to the same function c. Okay? So that's c times c dot. But two such terms, and the effect of minus sign goes away because the anti-commutator. This is c times c dot minus, well, if you didn't get it like this, minus c dot times c, and you pull it through, and you get something that looks like c times c dot. Okay? So one should do this more carefully, so on. But at least in structure, the answer is going to be from I, C, and C. Okay, so these are the BRST transformation. These are the suggested BRST transformation transformation properties for this point particle, for the action of the point particle. Okay, very good. Very good, very good. So, perhaps we should do what Lognardon suggested and check to see whether this action. Okay, so we should check to see whether we should just say small b minus 1 right, b minus 1 and perform multiplication. So one term of course is just b times b minus 1, which is this term, and the second term is bcc dot. So sorry, is what is y is b times the variation of e under a BRST transformation. Variation of e is the variation of e under the gauge transformation.
So it will be exactly like x.
Oh, no, not exactly like x, because e transforms like connection, like square root of connection.
Yes.
Okay, if it was exactly like x, it would be what Wilczynski has. But I think it's a second term will make like what we have. So it's the same calculation. You see? Let's do it. Okay, suppose variation of e under the BRST transformation was C times del E plus del EC. Okay, then we can group this up into del of C times E and integrate by parts, and it goes to this. Okay, but I think it is on this form, right? Because let's work this out. Well, the minus signs are always hard to do on line, but let's see this carefully. So how does E change under a coordinate transformation? Okay, so let's do it really carefully, just for difference. Okay, suppose we have T, and this is equal to T prime plus F of T prime. Okay, so we have E of T, and we want to relate that to E prime of T prime. Now, E transforms like a derivative, so because it has one index now. Okay? Exactly. EDT. Exactly. Let's do that. EDT should be equal to E prime of T prime. Okay? And so we find that now T prime dt, that's right, as T prime plus del F df of T prime. Okay, so we get that so E prime is equal to E plus del F of T times T. E prime of T, right. And therefore, E prime,
so now E of T, and this is E of T, now we put E of T prime plus F of T prime, and so you get another.
Exactly, this is the other term, and the other term is exactly del E times F, which you can write as del of F times E. Yeah. So that's what I was writing here, and then integrating by parts. I think it's probably just that. Okay, great. So what I have in my notes at least. Anyway, I should have checked my notes. Okay, great, fine. So let's move on. Okay, so now I'll check this more carefully. Kuczynski's book has many errors, but always makes me happy. We should check Lubboch. Do you know about this website by the way that Lubboch model maintains, in which he lists typos in Kuczynski's books? It's always useful when you think you have a mistake in Kuczynski, go and check against the model. You may or may not be right. Okay, good. So Kuczynski himself also maintains a website listing errors, half of which have been pointed out. Okay, so let's move on. Fine. So we've got some nice action and a BRST transformation property in this section. Okay. So now the next thing we want to do is to try to make this more useful. Okay. So this is now some hugely enhanced action, because in addition to the field, this E field that we added, we've also added this Lagrange multiplier field and all kinds of other stuff. Okay, so suppose we were to do the following. So, and then of course there are the host fields, the main sequence. So suppose we were to do the following. Suppose we were to integrate out the Lagrange multiplier. Okay, this would do two things. It would get rid of the Lagrange multiplier field, and it would send me to 1. We want to ask what happens to the BRST transformations under that process. Now, at first sight, it seems that it makes no sense to talk about the BRST transformations after we've done that procedure, because the variation of B, little b has a big B in it, and B is no longer a field in your action book. You do. Now, we define this one. But let's be a little more careful. You see, in integrating on B, we lose two fields. We lose E and B. Now, the equation of motion for this is another thing we could have. We could have integrated out E. All of A's with no derivatives in the action. Okay? And the equation of motion for E, which is sort of what we're losing when we eliminate these fields from the problem, determines B. Okay? It determines B in the following way. You see, so let's write down the actions. The action was this plus, and we'll stick to, for instance, case signs. So this plus I times B into E minus 1 plus E times B times C. I times B into E minus 1 plus E times, say, B dot C. Okay? Now, if we integrate out this B field, we lose the equation of motion that we would have got with respect to E. What is that equation of motion? That equation of motion is just differentiating with respect to E and putting E to 1. So it's just x mu dot x mu minus, that was a 2 here, sorry. Yeah, that was a 2 then. 2 plus m squared by 2 plus I times B plus B dot C is equal to 0. Okay, so therefore, if you do the following, if you do the integration out procedure, but replace this B here by what would have followed from these equations of motion. Okay? It sounds like you're doing something sensible. Actually, to derive this in a more satisfactory way, what you would want to do is the following. What you would want to do is take the path integral with this thing here, and then add alpha times B. See, because we want to keep track of what happens to a variation in B once we integrate out B. Okay? So suppose we take this path integral, add to it plus alpha times B, integrate out B, and then differentiate that resultant path integral with respect to alpha. What we have is the answer to what an insertion of B in the path integral would have been, even after it's been integrated out. Do you see what I mean? Let me say this again. Suppose you have a path integral and you want to insert a factor of B downstairs. One way of doing it is to take this action, add alpha times B to the action, and differentiate with respect to alpha. Differentiate the answer with respect to alpha. That gives you a variation with respect to B. Is this clear? Okay? So, now, suppose you want to know what the insertion of a factor of B would have been, even in a procedure after you integrate it out. This is an invariant way to do it. Okay? So, add this insertion into the path integral, then integrate B out, and differentiate the final result with respect to alpha, and then say alpha is 0. Okay? This gives you the same result as an insertion of B in the path integral originally would have, by definition. Okay? And I'll leave this for you as an exercise, but you can check that this procedure gives you exactly an insertion of this quantity, namely an insertion of the quantity that you get by replacing B with x mu dot by 2 minus n squared by 2 plus B dot C, all with a minus sign.
Alpha B insertion in the path integral will not have any E factor, right? How does it appear in that?
How does it appear in that? Right. Let's do it schematically. Okay, so what we're doing here is taking this path integral here and adding in an alpha times B plus alpha times B. Okay. Now the next thing we do is to do the integral over here. You see, where does alpha appear? Alpha appears in an additive shifting. Okay? So instead of setting e to 1, you set e to 1 minus alpha. Okay? differentiate that with respect, then you want to differentiate the answer with respect to alpha. Which is the same thing as taking the derivative of the action with respect to E at E equals 1, which is the equation of motion field. Is it clear? This is a more satisfactory way of seeing why that the equation of motion, from the point of view of the path integral, is the same, is the thing that is to be used for an insertion. Is this clear? Okay? Fine. So, however you do it, this insertion of this operator here, okay, is the same as the insertion of this operator once you integrate it out. Okay? So the BRST transformations in this new reduced theory, which has the BC ghost but otherwise has only the physical force, is delta of x mu is equal to IC x mu dot, delta of B is equal to minus I times x mu dot by 2 minus m squared by 2 plus b dot c, and delta c is equal to ICC dot. Okay, now these BRST transformations here, are, again, the algebra is more or less the same, but I want you to check that these BRST symmetries directly are symmetries of the action, but only on using the equations of motion. Okay, this is now not an on-shell, this is now not an off-shell symmetry of the action anymore. It's an on-shell symmetry of the action, essentially because you've solved for some field using an equation of motion. Okay, so I'd like you to check just explicitly that this thing is a symmetry of the action and that it squares to that it squares to 0 only once you impose the equations of motion, which of course is fine because we're interested in some operator relations inside a path integral, and equations of motion are true for operator relations inside a path integral. There's no problem in this true, but okay, good. So what have we got? We've got these BRST transformation properties in this reduced theory. I'm doing all of this because this is the analog of what we're going to be doing in string theory. But there'll be many more fields and it'll be less transparent. Okay? What we will want in string theory is to deal just with the x mu fields, the B and C courses, not these Lagrange multipliers and not the metric. Okay? So deal just with the x mu fields and the B and C courses, and yet deal with BRST symmetry. So we're doing the analog of this for the problem. Okay, great. Now that we have this nice explicit BRST transformation properties and nice explicit action for our theory, we can try to write down a formula. We can try to write down the formula for the BRST charge. Okay. So first, let's look at the action. So the action has remember E has been set to 1. So it has free scalars, okay, and it has a BC system. Now, the BC system is a quadratic path integral of anti-commuting fields of the type B dot C. Okay, the canonical interpretation of this path integral is that of a system such that the anti-commutator of C with B is equal to 1. How do we see that? Well, the canonical momentum conjugate to B is C. Okay? So, all I've written here is momentum conjugate to C, anti-commutator C is equal to 1. Okay? When we start dealing with the fermionic string, I'll have a lecture on fermionic path integrals in the Hilbert space interpretation, in which we discuss things like this in a more satisfying framework. But at the moment, roughly you see it from the usual rules of canonical quantization. And you just momentum with operator, commutator is replaced by anti-commutator anti-commuting fields is equal to 1. Okay, and when that is true, you know how to solve this problem. So this is you have to find the representation of this algebra and the representation of this algebra is clear. It's given by the operator 0, 1, 0, 0 and 0, 0, 0, 0, 1, 0. This is like the raising, one place is the raising operator, the other is the lowering operator, the two-state system. Okay. So what's the Hilbert space? We've got a path integral. What's the Hilbert space interpretation of the path integral that we have? The Hilbert space interpretation of the path integral that we have is that of free bosons for the x fields. Remember, 26 of them, or whatever, as many as there were both space and time coordinates, plus the two-state system corresponding to the B and C system. Okay? Now, the next question is what is the formula for the BRST charge system? Okay? Now,
okay, yeah, understand right here that BNC decoupling is that
no, with each other you mean?
no with the X.
Yes, they do. Because you see now when E is in set to 1, the action is just x dot squared plus BC dot. Okay? Nothing else is there. So it's two completely decoupled systems. Completely coupled. So just the two-state system plus the x fields. Okay? So what's the Hilbert space of the system? It's functions of d variables times up and down. Times vector in the two-state system of up and down. Okay.
So in that sense, it's not really like the BC, well, all the goes equal.
Yes, and it will be like string theory. It's the same thing happens in string theory. Right. Yeah, completely. There's no coupling between the fields and the coasts. Yes, completely. Yeah. But okay, yes. Yeah. Okay, so let's move on. So, good. So our Hilbert space is a state in this up, down, some state in this two-column CFD times some function of x mu, or equivalently in momentum space, a function of k. Okay, so the next question we could ask is now in this Hilbert space, can you write down a canonical expression? Can you write down a canonical expression for the Hamiltonian of our system? Sorry, for the BRST charge, BRST transformation charge of our system. Okay, so what do we want? We want something that when commuting with x's gives us c times x dot. Okay, and then commuting with b gives all this stuff. Okay, so the thing that works is and when commuting with c gives us all of this. So the thing that works is what? It is c times h, where h is equal to plus 1. Where?
There was an initial plus.
There was a plus here, you think?
No, okay. The initial Lagrangian should have been x plus square minus x square.
Okay, you think there's this minus sign somewhere. Then let me check. Okay. Something like that. Okay, so the C is active. The thing that would work would be something essentially of this form. Okay, so you see, for instance, if you take the commutator C times H with X, the momentum conjugate to X is X dot. So this you should think of as P mu squared by 2. So 1x will eat up 1p, you'll be left behind with a p, which is this guy here. And we have the c. If you take the commutator with a b, you'll basically hit this c and get everything else. And if you take a commutator with a c, you'll hit this b and get everything else. Okay. Now, on shell, using the equation of motion of the theory, you see, the term of the action has a b dot c or c dot b. It doesn't matter now whether you say n equals 1, equal after integration by parts. You use the equation of motion of the theory, and you get b dot equals 0, or c dot equals 0. Okay, so on shell you can just drop this term. It's important for generating commutation relations. But if you want to evaluate it on shell, some on shell action, this term is not there. Okay, so for many purposes, you can think of this BRST charge as just being c times h, where h is this quantity. Okay, now if we want to complete the BRST quantization of the point particle, what would we say? Well, we have to find the BRST cohomology of this point particle. Okay. So we want to find the BRST cohomology. So what can we do? Okay, so the BRST charge, so QB, is equal to C times H. Okay, and we're going to make this on-shell replacement where this thing is just, so that's C times x mu dot p squared by 2 minus m squared. You say there is a minus sign error. Okay, I'm going to ask you to forgive minus sign errors. The results will be an equation of motion which will be the correct equation. The correct on-shell equation. Okay, fine. So QB is this. This is the BRST charge system. Okay, so now let's make some notation. Let's say plus the up state is the state of the system that is annihilated by B, such that B on up is equal to 0. And so the down state is the state of the Lagrangian, such that C on down is equal to 0. And B on up gives down, and B on down gives up, and C on up gives down. Okay? So if we want to specify a state in the full Hilbert space of our theory, we have to specify whether it's up or down. Let's say, so the basis for the Hilbert space is up k mu and down k mu. Okay, so now what I'm going to do is to look at the action of this BRST charge on this basis. Okay, so we look at QP acting on, let's start by saying up k. Now QP has an explicit factor of C in it. C on up gives you down. So this is the same thing as down times k mu, and then you get whatever you get by acting h on k mu, which is k squared plus m squared by 2 plus minus whatever the correct thing for the equation of motion is. Okay, now we should be able to figure out what it is, because in Euclidean space, so we will back analytically continue, we should get minus k zero squared. Yeah, so this is correct in Euclidean space, so it's k squared plus m squared by 2, whatever that amount is. Right? Okay, good. Fine. So this is the actual QB on down on up. Fine. What about QB on down? On down times k mu. Now because down is annihilated by C. Okay, so we figured out the complete action of QB on the basis of our Hilbert space. So now the next thing we want to do is to list all states that are BRST closed. So BRST closed, that is states that are annihilated by the BRST operators. What are those? Well, it's QB down K mu. Sorry, it's down K mu for all K mu. And there are the states that are up K mu when K squared plus M squared is equal to 0. Okay, now how many of these states are BRST exactly? So let's look at this equation here. You see, every state that is of the form down K mu that doesn't have K squared plus M squared equals 0 is QB on something. Okay? So, down K mu with K squared plus M squared not equal to 0 is BRST exactly. Okay? So we're interested in BRST cohomology. We can find the basis, some class, equivalence class, some labels, some typical elements of the equivalence class of BRST cohomology. This is just generated by up K mu with K squared plus M squared, because this is closed and nothing that's of the form up is BRST exact, and also down K mu with K squared plus M squared. Okay, great. So now this is almost the answer. This is almost the answer that we got in the first couple of lectures of our class. Remember, the answer was all functions of K such that this equation of motion was obeyed. It's almost the answer because it's twice the answer. You see, we've got one set of functions with up and the other set of functions with down. Okay, so that's not quite what we had. That's not quite what we had in our discussion in class. Okay, this is an example of this phenomenon that in this method of BRST quantization we had a guess for what the right Hilbert space was, and it's a very reasonable guess. The guess is almost always a superspace of the correct answer, but it may be a little more, as we're seeing by explicit calculation. Now, I'm claiming that the correct answer, I want to claim that the correct answer in this case is which ones? Which were the ones that were exact? So down was exact. So I'm claiming that the correct answer is this.